Hello everyone. So I'm talking about thermalization in axion inflation. So this is work I've been doing with Alessio Nutari in Barcelona. So first let me thank the organizers for this little conference, for giving me the opportunity of speaking here. So even there is not so much time, I'll go straight to the point. So I'll discuss actions in inflation. So probably I don't have to motivate very much access to this audience. They are appealing way, in particular, they are appealing way of realizing inflation because they have this protection for the mass. This was long realized long ago, even by the members of the organizing committee of this conference. Okay, so this is the only ingredient I will need for the rest of my talk is this coupling here between axions and gauge fields, so known as the axial coupling. So I will consider phi to be the inflaton, and the gauge fields in the end they will be the standard model ones. So sometimes I might call it photon, although it could be also the non-abelian one. And so compared to the talks which we already heard about a similar topic, so the difference that here I'm not considering that the gauge fields have a belt. So they do not have a belt. And they are massless. So when phi gets a bev, because this term, the phi ff2, will break parity, the equational motion for the gauge fields is changed, and so here is for the two helicities, the plus and minus, equal polarization. So you can see the first two terms is just a plane. So you have the second derivative, k squared, and this is a term which is there due to the axial coupling. So you see that there's an instability. So one of the helicities will have an instability whose strength is given by this parameter chi, which is proportional to the velocity of the field, the rolling of the field. Okay, so the presence of the axion drives an instability in the equational motion for these photons, let's say. And there is an instability band. So for modes around the size of the horizon, a bit before and a bit after, they are exponentially enhanced. So they are in the vacuum, they are plane waves deep inside the horizon, and when they reach this band, by the expression of the universe, they are exponentially enhanced, and then they freeze up afterwards. And of course, so you can see here, at sub-horizon they are basically plane waves, but at late time, at super-horizon, they go to this e to the pi star, so they are exponentially dependent on these parameters. And of course, because of this exponential dependence, they can give rise to very interesting phenomenology. So they give large loop corrections, so loop corrections involving gauge fields in the loop to curvature perturbations, so both scalars and tensors, which are exponentially dependent on psi, and they can give rise to interesting ideas to generate large tensor modes, so some bumps in the tensor power spectrum larger than the vacuum through this shower of gauge fields. They could also back react or even preheat in the universe. So, but if this axion coupled to the gauge field does not decay, then it will leave an imprint on the CMB, and by observations we can constrain this parameter psi, which controls the exponential dependence, to be smaller than roughly 2.5, which is, you can see it as a lower bound on the scale f, which I think by the way is similar to what we heard in the talk in the first day by Isaac. Okay, so this is a super quick summary of what was done in this topic. So I will focus on what we did on this paper on archive. So there is this instability. So this instability produces lots of gauge fields. Some of them have momenta smaller than the horizon, where the particle interpretation is meaningful. And in fact, you can see that if you define this effective particle number just by the energy density of in Fourier space divided by the energy of per mode, which will be something of this form for the gauge fields, you see that the particle number is basically zero when the modes are deep inside the horizon, as it should. And when they are deep inside, when they are super horizon, they go to exponential of 2 pi psi. which can be a super large number. So this stability generates many photons, and so one can ask, so what happens when we have many of these particles around? Well, just because of the presence of the axial coupling, all these interactions are turned on. Scatterings which self-interactions between the gauge fields mediated by the axion, scatterings between two gauge fields to axions, and all of that. In particular, I will focus on this process, which is the most important one for what I'm going to say. So the scattering rate for this process, so here is the standard expression. So it's proportional to the amplitude of process squared. But there are phase factors, right? And these phase factors, so the process is enhanced if the incoming particles and outgoing particles are already populated, which is the case. So the phase space factors in this process will lead to an enhancement of number of particles to the cube. And of course, and for the decay it will be the number of particles squared, but of course there will be a threshold at which you have so many particles that the time scales between scatterings and decay is much shorter than the Hubble time, and the system should thermalize. And we estimated analytically this when does this happen, but also numerically. And we did numerically by deriving equations, Boltzmann-like equations for this particle number that I just presented you. And if you do that, you find out that the particle number, the equation for the particle number of the plus photons, ones which have the instability, gets a source term proportional to psi, which is the parameter which controls the stability. Okay, so but as soon as you and the others, so the axion and the other polarization are basically not sourced, are in the vacuum. So but as soon as you write in this form, you can now add all the collisions to the process. So that's what we did. We had all the processes that I showed before in the picture, involving phi and both polarizations of the gauge field. And we solved numerically. So the goal was just to check that the intuition was right, that you should get thermalization. So we get, so I'll just look at this plot on the left. Basically this is the particle number as a function of momentum. This dashed black line is the initial distribution. So you see that most of the particles that are on the left side, so are at very small moment, around the horizon size. But when you have such a large particle number or a small coupling, the system will thermalize, and that is that all the particle numbers between photons in max polarization, and the scalar phi, they overlap, which is in this line. And in particular, they overlap with the Bose-Einstein distribution, which we put there just by compute the energy of the system, and we plot the Bose-Einstein distribution. Okay, so we see that the system thermalizes. So numerically, we do this for a very range of a window of parameters for psi, which controls the particle number, and also for f, which controls the strength of interactions. And we find that the system thermalizes when this condition is satisfied. So this should be trusted, like to be order one corrections to this. So, but basically, psi has to be larger than 3.4 plus some function of f operation. However, so this would mean that even the inflaton perturbation would be thermalized. But if that's the case, you should impose more conditions. You should impose that the amplitude is the right one. And if you do that, you end up that psi needs to be 5.8. And this is a large number. So this has been shown to be, so there will be back reaction of gauge fields on the background. So you shouldn't trust it completely. And also higher loops start becoming important. So it's not in full control. However, we can overcome this issue very easily just by saying, okay, let's the gauge field be in the standard model. Because if they are in the standard model, there are many more interactions with fixed couplings. They are unsuppressed because they don't have powers of 1 over f. And it's more realistic because the inflaton anyway has to couple to the standard model. And so if you use the cross sections, so if you consider the gauge fields to be the photon, you consider photon fermion cross sections, or if it's a gluon-Cepheid interactions, you do the same type of analysis, and you get that you just need psi to be larger than 2.9 to get a thermal bath, a thermalization for the system under control. Okay. So, but what is interesting about this thermal regime? So, is that all the energy which was at horizon size is now moved to the UV, to the temperature scale. And this means that at horizon size the particle number is much reduced. And this will change completely what were the predictions on effects on curvature perturbations. So in particular, we found that in the thermal regime, the loop effects to the 2-point function of zeta go as the temperature will fall, so if all the energy in the system, in the photons, which was exponential, proportional to exponential 2 pi psi, goes into the thermal bath, which is the worst case, so you get that this loop correction goes into 2 pi psi, and you can compare with previous results where it was going as into the 4 pi psi. And more interestingly, all odd correlation functions will be suppressed because they will be proportional to the expression value of FF dual, and in a thermal bath, the parity asymmetry will tend to be restored. Not completely, because there is still some asymmetry in the spatial relations for the photons with plus and minus polarization, but most of it will be erased. So this means that constraints on psi will generically be weaker. Okay, but this is not yet the end of the story. So we have a lot of particles. This thermalizes the system. But is this thermal bath stable? Well, so when you have the thermal bath, the photons will develop a thermal mass, so proportional to the couplings and to the temperature. And of course, if the temperature is too large, so the mass will counteract with instability. And if the temperature is too large, it will just shield the instability band. So there will be no further production of gauge fields. So you can see here, this is the standard momenta, this is the axial coupling, and this is the generated thermal mass. So if this is too large, this will always be larger than 0, and nothing happens, so, which means that the bath will just redshift, the temperature will redshift away. However, it cannot redshift completely, because if it would redshift completely, the thermal mass will disappear, and the process will just restart, right? So the two things will have to balance each other, the instability and the thermal mass. And so, for this to be the case, so we have argued that the temperature should reach this equilibrium value where the two things are balanced. So you just have a narrow window where this becomes roughly equal or smaller than 0. And this corresponds to having an equilibrium temperature of psi h over g bar. So this is, I think it's remarkable because all the phenomenology was exponentially dependent on psi before. But now suddenly it becomes, in this regime, and once you get an equilibrium, it gets linearly dependent on psi. Okay, so we then try to, so assuming we reach this equilibrium stage, we try to find what were the predictions. So we still have to ensure that all the parts, so the inflow perturbations are normalized or through the standard model or not. And so this is the plot. The orange band is the region where phi is thermalized. The red is when you have back reaction, so where things are not so predictable. And the dashed is where the inflow perturbations have the right amplitude. Remember that because they are thermalized, the particle number at horizon crossing, it's not just 1/2, it's 1/2 plus the Bose-Einstein distribution, which horizon crossing you can just basically say it's T over H. So the scalar spectrum is amplified by T over H. On the other hand, the spectral tilt will be changed. So this is the standard minus 6 epsilon plus 2 eta, but now there are time dependence on the temperature. So because the temperature is linear on psi, and psi depends, so you can write psi as a square root of epsilon, this lower parameter. This will give you, instead of minus 6 plus 2 eta, it will give you minus 4 plus eta. So this is the prediction of this case. And the tensor to scalar ratio will be, in this case, suppressed because the scalar spectrum is enhanced. And because the tensors are much harder to thermalize because they have rotational couplings, so the tensor to scale ratio will be suppressed by 1/psi, which will maybe helpful to make some models of large field models of inflation more compatible with it. So regarding non-Gaussianity, so we have estimated what would be the loop correction in the thermal case, and we found that at most it should go as the temperature to the 5. But this coefficient is still, we still don't know what it is. We should do a more precise computation of the thermal case, including the expansion of the universe, because it could already constrain some of the region. Okay, and I conclude. So here we generate a thermal bath for inflation, which seems to be under control. Just created by the axial couplings, so it's a very simple system. It's just the photon and the standard model particles. So the couplings are shift symmetric. So this means that there should be no thermal masses for phi, which is a strong protection for the axiom. And so the prediction, once you reach this thermalized stage, the prediction should be the predictions are changed. So both the constraints on psi, and so if d photon is thermalized, we have this prediction for the spectral field, and R will be generically reduced. So to be done, we still have to show explicitly what would be the final distribution after we reach this temperature, and also improve the non-Gaussianity computations to get more precise constraints. And maybe because it is back reaction regime, all the inhomogeneities. So before we had all the inhomogeneities at the horizon scale. That's where the photons are. But now we moved everything to the UV, to the temperature scale, and so it might be better under control to make a back reacting. So to have gauge fields back reacting on the photon and allowing for inflation on steeper potentials. And possibly maybe different features to study like oscillations and things like this. Thank you.